For the electric circuits laboratory, the experiment 5, which is named as capacitor, will be realized. The objectives of the experiments are validating conclusions regarding the behavior of capacitors in a steady-state DC network, and secondly, plotting the exponential curve for the voltage across a charging capacitor. Thirdly, verifying the basic equations for determining the total capacitance for capacitors in series and parallel. And lastly, demonstrating the usefulness of Thevenin's theorem for networks not having the basic series RC form. The equipments will be used in the experiment are resistors, capacitors, multimeter, a board and voltage supply, and a chronometer. For part 1, basic series RC circuit will be realized. To do that, the circuit is constructed as seen in the figure in the manual. 10 DC volt power supply will be connected to the circuit. A resistor which has a nameplate value of 1.2 kilo ohm is inserted in the circuit, but before that the actual value of resistor is measured and noted as 1.176 kilo ohms. So we will connect the power supply to the circuit, and in part C, the voltage across the resistor will be measured. And noted as 0.4 millivolts. Also, the voltage across the capacitor will be measured. And noted as 10.01 volts. For part A, carefully disconnect the supply and quickly measure the voltage across the disconnected capacitor. Is there a reading? Why? So we will disconnect the supply, and the voltage across the capacitor can be wrote as 9.97 when the value we first see. In part F, short the capacitor terminals with a lead and then measure capacitor voltage again. So we can touch the leads of capacitor to each other. And we can note the value as 0.01. In part 2, we will construct a network in the figure. $1.2 kilo ohm resistor will be stay here. Then we can write the actual value of this resistor again as 1.176 kilo ohms. Same with the previous. And secondly, we will use another resistor which is measured again. And we can write the value of 3.21 kilo ohms as its actual value. And a capacitor will also connect it. In part C, it says energize the system and measure the voltage 1, voltage 2, and voltage 3. Calculate the currents. So voltage measurement will be done. First voltage measurement will be from 1.2 kilo ohm resistor. Second one will be from the other resistor, and third one will be from capacitor. And we will note the values. As a first voltage value, we can write 2.68 volts. For the second value, we can write 7.32 volts. And as a third value, the voltage across the capacitor will be noted as 7.32 volts. For part 3, series and parallel as RC-DC network will be realized. In part A, it says construct a network of figure and insert the measured resistor values. So again, 10 volts of DC voltage source will be used. 1.2 kilo ohm resistor will be stay. Another capacitor will be at near the second resistor. So we can use the first one. A 100 microfarad capacitor. And then second resistor will be connect. And a second 100 microfarad capacitor. Will be connected as parallel combination. We can write the value R1 as 1.176 kilo ohms, and for the second resistor we can write the value as 3.21 kilo ohms. In part C, it says energize the system and measure the voltages V1, V2, and V3, and V4. So for V1, we will measure the voltage across the first resistor. For which we can write 2.4 millivolts. For the second voltage value, we will measure the value on the second resistor. For which we can write 1.1 millivolts. For the third voltage value, we will measure the voltage on the first capacitor. For which we can write 9.99 volts. And as a last voltage value, V4, we can write the value of 10 volts. In part 4, the actual capacitance of the capacitor will be determined. To do that, we will use 10 volts of DC power supply and a 100 kilo ohm resistor. Firstly, we can measure the actual value of resistor. And we can note that value as 98.1 kilo ohms. I will use one end of this resistor as a switch, so I will not connect one end. Or we can just use a switch. Like that. Then a 100 microfarad capacitor. will be added to the circuit, and voltage value on the capacitor will be measured. But firstly, let's connect two ends of capacitor to each other. To discharge the capacitor. And in part C, before turning on the power supply or closing the switch, be sure to discharge the capacitor by placing a lead across its terminals, then energize the source, close the switch, and note how many seconds pass before the voltage VC reaches 63.2% of its final value, or 6.32 volts. So we will count to time when we see the voltage of 6.32, we will stop counting the time. So as I connect the switch, I will start counting. Okay. I am discharging the capacitor. As I connect the switch, I will start counting. I see the value and I stop the time. So for 100 microfarad capacitor that I used, I can write 9 seconds, 9.44 seconds. I will do the same procedure for the other capacitor, which has a value of 220 microfarads. Before I start, I will discharge the capacitor. And as I connect the power supply, I am starting to count until I see the value of 6.32 volts. And for that capacitor, I can write time constant as 22.18 seconds. In part 4, additionally, a second 100 microfarad capacitor will be used, because in the next chapters you need to use 100 microfarad capacitor in a one circuit. So I will repeat the same part with using another 100 microfarad capacitor. So I will connect the capacitor to the circuit. Before I measure a time constant, I will discharge a capacitor. As you can also see from multimeter. And as I connect the power supply, I will start counting. And when I see the value of 6.32 volts, I will stop counting. The value can be noted as 10.58 seconds. For part 5, charging network of parallel capacitors will be realized. To do that, we will construct the network of the figures. The power supply of 12 volts will be applied to the circuit, and a 100 kilo ohm resistor, which is having an actual value of 98.1 kilo ohm, will be used. A 100 microfarad capacitor and 220 microfarad capacitor will be connected to the circuit as a parallel combination to each other. The minus ends of the capacitors will be at the ground. For the values of capacitance, we will use the measured ones after our calculations. So for part E, it said, using a watch, record the voltage across the capacitor at the time intervals appearing in table after the switch is closed. We will measure the voltage value on the second capacitor. Before we start, we will discharge the capacitors. And as I connect the power supply to the circuit, I will start counting, and with time intervals like 10 seconds, 20 seconds, 30 seconds, I will write the voltage value across the first capacitor, a second capacitor, and also first capacitor. So I will repeat the procedure again for the other capacitor. Firstly, I will start with I will repeat the procedure again for the resistance. the voltage on the resistor. No, I will not do that procedure again. It is just a calculation. So it will be measured only on this capacitor. So as I connect the power supply, I open the switch of timer and the value is 3.47. At 20 seconds the value of 4.71. At 30 seconds 7.33. For 2 seconds 8.56. 50 seconds 9.38. A minute and 10.01. 7 seconds 10.49. 10.80. 90 seconds and 11.04. 100 seconds and 11.90. 11.32. 2 minutes 11.39. 11.44. 11.48. 11.51. 11.54. 11.56. When it is 3 minutes, it is 11.58. And 11.60. And when it is 200 seconds, it is 11.62 watts. For the part 6, charging network of parallel series capacitors will be realized. To do that, we will construct a network of the figure and we will insert the measured resistance and capacitance values. Firstly, a 100 kilo ohm resistor will be used as R1. So we can use the resistor which we already know the value of its resistance. So we can write it as 98.1 kilo ohm. As a second resistor, another 100 kilo ohm resistor which will be used. And for that one, we can write it is 99.1 kilo ohm. With a series combination to the first resistor, and we will use two capacitors. One is 100 microfarad, which the measured value of that capacitor will be used. And as a second capacitor, another 100 microfarad capacitor will be used with a series combination, and minus end of this capacitor will be at the ground. This time I will measure the voltage across both capacitors. I will use the first end of the first capacitor and the last and minus end of the second capacitor. And in part E, it says that using a watch, record the voltage across the series capacitors at the time intervals appearing in table after the switch is closed. So to do that, we will open voltage source of 12 volts. And as I connect the supply, I will start counting and I will read the value. Before I start, I will just discharge the capacitors. Five seconds and the value is 5.58, 7.32, 9.36, 10.22, 10.82, 11.40, 11.52, 11.60, 11.66, 11.70, 11.75, 11.76, 11.76. And at 100 seconds it is 11.77. For the last part of the experiment, Thevenin's theorem will be applied to the circuit. To do that, voltage source of 16 volts will be used and 100 kilo ohm resistor, which is having an actual value of 98.1 kilo ohm, will insert it to the circuit. And a second kilo ohm resistor, second 100 kilo ohm resistor, which is having a 99.1 kilo ohm, will be connected. Then a 47 kilo ohm resistor. Before we start, we can see the actual value of it. And we can write 46.3 kilo ohm. Will be connected. I will use one end of this resistor as the switch, and 100 microfarad capacitor, the first capacitor, will be connected. The minus end of the capacitor will be connected to the ground. With the calculations, you will calculate the time constant, and for part F, close the switch for the network of figure and record the level of voltage on the capacitor after one time constant. So firstly I will connect the power supply, because the switch is open. I can connect it now. I can discharge the capacitor. And the voltage value on the capacitor will be measured. As we switch the switch off the circuit, I will leave the data for you. You can see the voltage value across the capacitor as time is passing. So with your calculation, you can find the one-time constant. And as you see the one-time constant here, you can note the value of voltage